Every day, millions of us drop our phones onto wireless charging pads without giving it a second thought. It feels like magic, but in reality, it's a beautiful real-world application of vector calculus and electromagnetic field theory. Welcome to our experiment project presentation. Today, our group is going to peel back the curtain of this technology by building a localized mid-air wireless power transfer system completely from scratch. The core objective of our experiment are threefold. First, to practically demonstrate how electric currents can generate magnetic fields and how those fields can induce voltages across space without any physical electrical contact. Second, to understand the engineering challenge of converting static DC current into a time-varying magnetic field using a high-frequency transistor oscillator circuit. Third and finally, to analyze how spatial geometric constraints, specifically distance and angular orientation, which will affect magnetic flux linkage and transfer efficiency. To show you how we transition from abstract equation to a working prototype, I will hand it over to my teammate to explain the underlying physics and circuit architecture.
Hi Doctor, my name is Eugene, and now I will be explaining the circuit that will be used in our experiment. So for our circuit, it consists of two circuits. The left side is the primary circuit, and the right side is the secondary circuit. The first circuit is used to generate an AC source from the DC source, and it uses the characteristic of a PNP transistor. So firstly, since there is no base current here, so the current will flow from the positive terminal through the base and back to the negative terminal. And after there is base current, the current will flow from here and from the collector points to the emitter points and back to the negative terminal of the cells. And after this, it will goes back to the base current and then back to the negative terminal. And this process, it keeps repeating and produce a AC source on this point. So after an AC source is generated on the coil, it will generate a changing electromagnetic field. And this changing electromagnetic field will change the magnetic flux in the secondary circuit. This changing electromagnetic flux will produce a EMF on the secondary circuit based on the Faraday law. And the produced EMF will produce a current. And this current will light up the LED bulb on the secondary circuit. So next, I will be explaining the material that will be used in the experiment. So we use a battery cell holder to hold the DC source and two coils that is made out of copper wires. So these coils with two terminals is used in the receiver side on the secondary circuit. And this coil with three terminals is used in the primary circuit. So the two terminal here is the two ends of the copper coils, and the middle here is coming from the middle points of the copper coils. And right here, we got a transistor to generate an AC source and a resistor to produce the base current, and also a LED to indicate the successfulness of the experiment. So following the procedure, first, we connect the positive terminal of the battery to the collector of the transistor, and we connect the transistor, the base of the transistor to the resistor. After that, we connect the negative terminal of the battery to the middle point of the coil. And we connect one of the two ends of the coil to the resistor, and another end is connected to the emitter of the transistor. After that, we connect the two pins of the LED to the coils, or as it is as a secondary circuit. And we place the first circuit inside the box and the secondary circuit on top of the box. So by putting as this, we prove that even without direct contact of the coils, the current still successfully be generated on the secondary coil. And next, I will be showing the demo of our experiment. So right now, this is the box that containing the primary circuit, which generate the AC source from the DC battery. And right here is the secondary circuit, which consists of the white LED and also the secondary coil. So now, the two circuit is separated, but as I put the coil close to the primary circuit, we can see that the LED lights out. But if I move the coil far away, you can see that the intensity of the light bulb decrease. And another thing to notice is that if I place the coil in a degree of 90 perpendicular to the primary coil, the LED lights will also turns off.
Hello everyone, my name is Hufangi. Now I'm going to explain how the experiment is considered success. The answer is by observing the LED light up or not. So basically from the demo video, when the coils were placed close together to each other, the LED was able to light up. So this means the experiment is considered success. Now, what is the distance between the coils changing? So from the demo video, if the distance increasing, it will result in the induced voltage reduced. So the LED become more darker, and vice versa. If the distance decreasing, it will result in the induced voltage increase, and the LED become more brighter.
Hello everyone, my name is Lau Ting Feng, and now I want to share with you about the brief summary of this experiment. So in conclusion, this experiment successfully demonstrated the principle of wireless power transfer through mutual inductance. When an alternating current flows through the transmitter coil, it creates a changing magnetic field. This changing magnetic field induces a voltage in the nearby receiver coil, allowing electrical energy to be transferred without direct electrical contact. The LED was able to light up when the coils were placed close together, showing that energy was successfully transferred wirelessly. So therefore, the objective of this experiment was achieved as we successfully demonstrated electromagnetic induction and wireless power transfer. And besides, I want to discuss about the limitations and applications of the mutual inductance. Although the experiment was successful, it has several limitations. The distance between the transmitter and receiver coils must be very small for efficient power transfer. As the distance increases, the magnetic coupling becomes weaker, causing the induced voltage to decrease and the LED to become dim or stop lighting completely. In addition, poor coil alignment, fewer coil turns, and lower operating frequency can further reduce the efficiency of power transfer. Despite these limitations, wireless power transfer has many practical applications. It is widely used in wireless charging pads for smartphones, electric toothbrush charging, smartwatches, and wearable devices, RFID systems, medical implants, and is also being developed for wireless charging of electric vehicles. These applications demonstrate the importance of mutual inductance in modern technology.